I want to show you that there exist other functions, presuming you're allowed non-negative real valued functions. So here's a claim. I'm going to prove for you that 1 over n is little o of 1. So we're going to try proving this. So we're going to try proving this in two parts. So remember, we had our first definition and then our second definition. The second definition is where we take all the logic out of our first proof and we kind of slam them together in a logical conjunction. So we bring them together. It's them put together as an and. Sorry, I'm getting a little excited here. My point is that they slam together, kind of like a really epic Kool-Aid commercial. So remember that our definition was that we have, if I have f is little o of g, this means this is no different than me saying that f is big O of g, and it has to be both this and that f is not big theta of g. But remember, as we talked previously, the whole thing is going to be set up where if that's the case, and we know that the definition of big theta is that it satisfies big O and big omega, then it has to fail for big omega. So this is actually me saying that f is not big omega of g for our proof. So just keep that in mind when we walk through this example, because it's going to be an important setup for how we're going to break this into cases. So I'm going to first show you that we can satisfy the big O part, and then I'm going to show you that you can satisfy this second part that says it's not big theta. If we can do that, then we've satisfied the little o claim that we need to prove. So proof, well, let us prove this in two parts. In two parts, I'll say two with the word. In two parts via the definition. So let's look at the first part. Let's first prove that 1 over n is big O of 1. So what do we have to do if we're trying to prove the big O claim? We need to find constant c, which is a positive real number, and n0, which is a positive integer, such that 1 over n is less than or equal to c times 1 for all n greater or equal to n0, correct? That's what we need to do. So let's write that out. We find constants. Constant c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, 1 over n is less than or equal to c times 1. Okay. Now here's a beautiful part. Let's see what 1 over n actually looks like for different values of n, just to convince ourselves of the following thing, just in case you forgot how fractions work, because you never really know what happens in your day, okay? All you can have is the funniest of brain farts, and then suddenly you forget how fractions work. So anyways, well, 1 over 1, that's 1, right? This is equal to 1. The next term that would be in this would be 1 over 2, that's 1/2. The next one would be 1/3, next would be 1/4, and so on. Notice that all of these are less than or equal to 1. It never gets bigger than 1. It's always less than or equal to 1. So let's use that information. So notice that this on the right-hand side is going to be 1 if I let c be 1. So that's how I'm going to pick c. Pick c is equal to 1. Then observe that for all n greater or equal to 1, that 1 over n is less than or equal to 1. So choose n0 is equal to 1. Therefore, by the definition of big O, so now let's invoke the definition of big O. Therefore, by the definition of big O, 1 over n is big O of 1. That's the first part of the proof. So we got the first part. What's the second part? The second part is the proof that f is not a big theta of g, or in our case, that 1 over n is not big theta of 1. So remember, we've established this first part, which is actually a part of the big theta definition. So 1 over n is not big theta of 1. That's the second part of our proof. We showed in 1, so the first part, that 1 over n is big O of 1. So by the definition of big theta, so what does that mean by the definition of big theta? That means that it must be the other condition of big theta that went wrong. By the definition of big theta, it has to be that 1 over n is not big omega of 1. So now let's take the negation of the big omega definition using the same game we've seen in previous lessons. So remember, in big omega, if we try to prove a big omega claim, we have to find the two constants c and n0, similar to our big O claim that we had over here, except you would have it where the inequality is a greater than or equals as opposed to a less than or equals, right? So the question is very natural. When you flip it, make it a negation of that claim, then you're going to have arbitrary c and n0 given to you, and you have to show that you can always find that n such that f of n is strictly less than c times g of n, as opposed to greater than or equal. But you have to pick n big enough such that it's greater or equal to n0, right? So then, by the negation of the definition of big omega, for any c, it's a positive real number, and n0, that's a positive integer, we find n greater or equal to n0 so that 1 over n is strictly less than c times 1. So now what we need to do is we need to presume that we're given c and n0 that are arbitrarily fixed. So presume c and n0 are arbitrarily chosen and fixed. So we need to make sure we can satisfy this inequality no matter what c and n0 are. So remember, the whole game is that they give you c and n0, and you have to give me an n that always works. If assuming that they said, hey, look, 1 over n is actually big omega of 1. So they have to show you, they give you these two constants, you have to show how to refute it. So let's think about this. So next, let's try to find n. To find n, notice that, so this is usually the part of the proof where you try to do some clever thinking. So notice that it's 1 over n is less than c times 1. And c times 1 is just c, right? But also remember, c and n0 are both positive, right? They can't be 0. So what does that mean? That means that I can multiply both sides of this inequality by n, and then I can divide both sides of the inequality by c. To find n, notice that 1 over n is less than c if and only if. So I'm going to use this double arrow to indicate if and only if. So this is just done via the steps I just mentioned algebraically. Less or equal to 1 over c is less than n. So now that you can see that now I can get n on one of the sides of the inequality, now I just need to come up with a sufficient upper bound on 1 over c. And then I pick n to be appropriately large. And for any c greater than 0, so we have 1 over c. Okay, I'm going to try making something that's bigger than 1 over c. So one natural way I can start is I'm going to try to make it into something, because remember, I have to find n. And n is an integer, right? It's a positive integer that's greater than or equal to n0. So I can't just simply make it so it's c. C can potentially be a fractional number, for example. So 1 over c, what I'm going to do is I'm going to make it so that when you carry out 1 over c, you're going to round that up to the next highest integer if it has a fractional part. So what I'm going to do is I'm going to introduce the ceiling function. So 1 over c. Now, if you've never seen the ceiling function before, it works like this. So if I give you, say, 2.5, you would write down 3. If I give you a 2 inside of the ceiling, it's a 2. If it's 2.01 with a ceiling around it, it's 3. It rounds up to the next integer. If there's a fractional part, the easy way to describe this is you always round up by default. If you have a fractional part like this, you're going to round up. This is in contrast to something called the floor function, where you take and scrap off the fractional part, and implicitly you're rounding down. So if you have an integer, you end up with the same integer. If you have a number with some fractional part on it, if it's a floor function, so this is the ceiling function, just to be clear. So this is the ceiling function, or ceiling. You always round up. So naturally, if I take 1 over c, and then the result of that I'm going to round up, I end up with either the same value or greater. Then, naturally, I want to make this a little bit bigger. I want to make it a little bigger than this, because remember, I need a strict inequality. That's what I'm required to get, is a strict inequality, like I have here. I need to make sure whatever I get as a result of this is going to be strictly less than n for the sufficient, when I pick n. So it has to be that n is greater or equal to n0, and it has to be that this inequality actually holds for that particular value. So all I'm going to do is I'm just going to tack a 1 on, just to make it slightly bigger. So this is indeed an integer, but I must stress that this statement in itself doesn't require it to be an integer. I'm just saving myself a little time, because all I'm going to do now is I'm going to select n. And now remember that I need to pick n such that n is greater or equal to n0, and it has to satisfy that inequality over there. But what did I say here? I actually gave you a way to pick n, right? If I pick n to be this, then this inequality is going to get satisfied, no matter what c is, because c, it could be any value greater than 0, and this will be satisfied. So what I'm going to do is I'm going to use a max function. So I'm going to take the larger of these two values. So I need n to be greater than or equal to n0, so I'm going to say n0. That's one of the choices. Or it's going to be the ceiling of 1 over c plus 1. So whichever of these is the larger one, you pick that as n. That's the recipe. Therefore, by the negation of the definition of big omega, 1 over n is not big omega of 1. Now, since we have the two parts now we can say therefore, by the definition of little o, it has to be that 1 over n is little o of 1. And that completes the proof.